Hello everyone! There are only a few days left until the end of 2025, so I'll release one more video tutorial this year. Once again, it will be a contribution to the category of scene transitions, and as you can see right now, rotating vertical tiles look quite impressive. So let's go ahead and program it. And because this is a transition, we will once again need two background images, which I'll again borrow from our game Whispers of Prague. So I'll create the usual 2D scene with all the elements that belong in it. Right-clicking the scenes folder, create new scene, and it should be 2D scene, and let's call it wave transition. Okay, and as usual, I'll drag the screenshot found in JPEG into it, so the sprite 2D node was automatically created, and in the inspector we'll do the usual stuff, expanding offset and cancelling centered, then expanding transform and resetting position to 0, 0. Now I will scroll down to the material section, create a new shader material, click it and create a new shader, which is called wave transition.gd shader, type shader mode canvas item, and the folder will be as usual shaders. Okay, create and clicking again to open it in the editor. Alright, and as always, I'll delete everything we don't need. I mean everything from the generated code that is not a fragment function. So deleting vertex and deleting light, and Ctrl S to save. Okay, so let's start with the parameters, which are an important part of every good shader. We'll only need 4, so I'll write them down right now. First, we'll need the target image, which I'll name target as always, and I'll give it the hint default black hint in case this parameter is left empty. Let's do it here. Uniform sampler 2D target and the hint default black. Okay, and I'll immediately insert the usual image into it so we don't forget later. Where is it? Here, chapter JPEG. Also, let's expand shader parameters and drag it into it. Let's continue. As you've surely noticed, the effect is based on dividing the image into identical vertical sections, so we need to define their count. Uniform float tiles with a hint range, and the initial count let's set to 10, and the range will be from 1 to, for instance, 20, and the step is of course 1, no fractional tiles. Okay, and because this is a transition, we must know at which stage of this transition we currently are. So this would be the third parameter called phase. Uniform float phase with a hint range, and the phase starts at 0 and it goes from 0 to 1 with the step point 0, 1. Finally, I'll add an option to set the background color, which becomes visible during the rotation of individual tiles. We could probably make do with black, but someone might prefer a transparent background so the effect blends better with the game environment. So let's do it here, uniform vector 4, because not just the RGB color, we need RGBA with the alpha channel. Let's call it back color. Let's give it the hint source color to show the color picker in the inspector, and the initial value let's set to black, opaque black, so 0, 0, 0, and 1 for the alpha channel. Okay, so we now have all parameters ready and can move on to implementing the fragment function. As we saw at the beginning of the video, the effect progresses from left to right, so this time it's not symmetrical around the center, and therefore we don't need to shift the coordinate origin. I'll simply assign the UV coordinates to the UV vector. Back to UV is UV. Next comes dividing the image into tiles. As you may remember from previous tutorials, we use the floor function for this purpose, which returns the integer part of a number. So I'll write this code and then explain it. UVX is multiplied by the parameter tiles and float tile ID is floor, as I said, of UVX divided by tiles, semicolon. Okay, so what do we have here? You may recall from previous tutorials that to divide an image into a grid of tiles, we usually multiply the UV vector by the number of tiles. But this time, the division is only in the vertical direction, so multiplying just the x coordinate is enough. And to have some output from this function, I'll write the skeleton of the code responsible for it. So vec4 color would be back color as the initial value. Then we'll do some calculations, and after them, color would finally become texture of our texture and the transformed UV coordinates, which means lowercase, of course. And finally, let's define the output. Color is simply color. Okay, very well. Something happened. I'll get to that very shortly. Notice that this time we get it from the image texture using the transformed UV coordinates in lowercase. That's because, unlike many other effects of this type, we are also modifying the source image, so we must apply the transformations to everything. As we can see, the image has shrunk into a single tile here on the left. This is because at the beginning of the code, we multiply the x coordinate by the number of tiles. So to get the original image back, we need to divide this by this number. So let's do it here. Okay, so this is the multiplication I mentioned, and now I will do this. UVX is divided by the number of tiles. Okay, now we are ready to apply our algorithm to the individual tiles. Because we will be rotating them, we need a function that performs a 3D rotation around the y-axis. If you watched my series on ray marching technology, you may remember that we used such functions there, and those functions were based on 3x3 matrices that we multiplied a three-dimensional vector by. This time, however, we'll use a slightly different formula because this shader contains no 3D objects, it's 2D. So I'll write the function first and then explain it. Okay, let's do it here, and I'll call it rotate y, and it returns vector 2. Rotate y, and the parameters are vec2 UV coordinates and float angle for the rotation. Okay, and now vec3 result is inverse of mat3, the matrix, and it consists of three-dimensional vectors. So vec3 cosine of angle 0 and negative sine of the angle. Okay, the first vector, now the second one. Crap. Vec3, 0, 1, 0. Okay, and finally, vec3, 0, 0, 2. All right, and this matrix will be multiplied by a three-dimensional vector. Vec3 UV for first two coordinates and minus 0.5 and 2. Okay, so this is the vector, the resulting vector, and now we need to return return the two-dimensional vector, so we will transform it like this. Result.xy divided by result z plus 0.5. Okay, so this definitely needs an explanation. So what's happening here? As we can see, just like in 3D and remarching shaders, we have a 3 by 3 matrix, this one, multiplied by a vector 3, which resembles the usual rotation around axis formula. But notice the inverse function we apply to the matrix. I think this is the first time I've used it in any shader, and this function returns the so-called inverse matrix, a concept from linear algebra, whose definition and description I won't spend time on here. All information can be found on Wikipedia. For the purposes of this tutorial, the important thing is that we are performing the rotation in the opposite direction, because instead of rotating a 3D object, which we don't have, we are rotating an imaginary camera that is viewing the 2D texture. And we want to rotate around the tile's axis, not its edge. To achieve that, we need to subtract 0.5, this is it, from the UV coordinates, local coordinates, perform the rotation, and then add it back when we form the result. And the operation in this last line projects rotation back to 2D, because the result must be vector 2, not vector 3. And notice these 2's here and here. That's unusual, because rotation matrices usually contain only zeros and ones. The reason is that this operation causes perspective distortion, so we compensate for it this way to make the final effect look more realistic. Later we can show what this distortion looks like. Okay, so now we are done with the rotation function and we can apply it. First, we'll need the angle of rotation, which we will control using the current value of the face parameter, and also the tile ID variable, so that the subsequent tiles rotate with a slight delay, this one, creating something like a wave effect, like this. Okay, so float angle equals clamp of face minus tile ID, and clamp it to the range from 0 to 1 times tau. Alright, so I use the clamp function because the result of this subtraction might go into negative values. And because we want angles in the range from 0 to 360 degrees, I multiplied the result by tau, which is the same thing but in radians. So it is basically a full circle. Now we recalculate the UV coordinates using our rotation function. And because it works with the local coordinates of a specific tile, we must pass the corresponding parameter, like this, so it won't be UV, but a fractional part of UV. Let's do it. UV equals rotate Y, and now the parameter fract of UV, and our angle. Okay, now something has changed. Let's show more of that. We can see the individual tiles, and when I change the face parameter in the inspector, we can also see some rotation. Okay, but a few steps remain to reach the final result. And the first one is to ensure that not all tiles display the same part of the image. We'll achieve this by adding tile ID to the x coordinates at the end. So let's do it here. It should be right here. UVX is increased by the tile ID. Okay, very well. That's already better. Let's try changing the face again. But it seems that the tiles are not limited to their width. You can see it here, like it is too wide, I guess. At least from the perspective rendering point of view. So we'll fix that by displaying their content only for the transformed UV coordinates that fall within the interval from 0 to 1. Okay, so what we have to do is to simply wrap these lines into this condition. If UVX is greater or equal to 1, and we'll simply wrap it to this 0 to 1 range, UVX 1 and UVY and UVY, okay, and this. And I'll fix the indentation. All right, excellent. So let's try it again. Face. Yeah, I guess we could be satisfied with the shape of the rotating tile. Now we need to ensure that it rotates only once around its axis and then stops. So we'll add a rotation limit of 180 degrees. So where we define the angle here, and let's clamp it. So angle would be clamp of angle and 0 and pi, which is the half circle, 180 degrees. Let's try it again. Changing face, and yeah, now all tiles rotate just once, but it seems that some of them don't make it to the end. So to achieve the correct motion for the entire image, we'll speed up these rotations a bit by multiplying tile ID by 0.5 times 0.5. Okay, and now to reset and do it again. Yeah, now it's perfect. So we solved the rotation, and now we need to do something about the backside of the rotating tile. The target image should appear there. So we'll define a flip function, the flip variable, based on the current rotation angle. It will have the value 0 for the first image and 1 for the second. Okay, let's continue after the clamped angle and define float. Flip is 0, and if angle is greater than pi divided by 2, which means 90 degrees, let's set flip to 1. Okay, and we'll use this value in the usual way with the mix function, which returns a pixel from the first or second image. So instead of just color this, let's enhance it. A mix of texture, and I'll copy paste to speed up the process. This time it's target, and the weight value would be our flip variable. Okay, and let's try it again. Yeah, it's changing to the second image, but of course it seems the second image is displayed mirrored on the tiles. So we need to adjust the local x coordinate. Let's get back to the flip definition, and in this case UVX would be reassigned to 1 minus UVX, and it should fix it. Yes, let's do it back. Okay, I would say we are done. We can play around with the parameters. The number of tiles can be changed and the result should still be satisfactory. For example, let's make it 20. Yeah, it looks pretty cool. And if we want to simulate the rotation of the entire image, we just need to set the tiles parameter to 1 and rotate it. Perfect. Okay, by the way, we can demonstrate how small changes in the rotation function influence the overall effect. But before I proceed, I noticed that I have a small bug over there. The rotation should happen before we flip the coordinate, not after. So let's cut this line and paste it over here before the flip definition. Now when I try the face again, it should rotate correctly. Yeah, everything is in the same direction. Sorry about that. All right, and now, as I said, the rotate function, so let's scroll to it. And if, for example, I change the unusual twos right here into ones, we'll see what happens to the perspective. So let's rotate some of these tiles and change it. 1 and 1. Okay, can you see it? Now, when we observe the transition, we can clearly see how distorted the perspective is. And it's precisely why we use the doubled constant. So if I change it back, it should be correct again. Perfect. And what would happen if we removed the shift of the local coordinates, which means subtracting 0.5 here and adding 0.5 here? Let's do it. So deleting and deleting. Okay, and now when I use the face parameter, we can see how the tiles rotate around the axis. Around the edge, not the axis, vertical, which completely breaks the effect. So let's put it back. Okay. Very well. And I guess that's all. Thank you very much for watching. I think we wrapped up this year 2025 nicely with this useful effect, and it will certainly find its place in many games. Next year, 2026, I definitely want to continue publishing tutorials, but they won't always be about shaders. I also plan to create something about modeling in Blender and using finished models in the Godot engine, including various optimizations, a topic I've been working on over the past few months and have really started to enjoy. We'll see how much time I'll have for everything. For now, take care, good luck with your projects, and I'll see you in the next video.